In this video, we're going to go over efficiency of energy conversions as well as thermal stability. So I'm first going to go over these notes down here, and then I'll talk about this diagram up here. So efficiency is a comparison of the amount of energy that we put into a system and the amount of useful energy that we got out of the system. So you should know what efficiency of a system is. Another way to say this is that for efficiency, we're comparing the amount of energy available in a substance with the amount of useful energy that we can get out of that substance there. Okay, so the formulas for efficiency, there's two different forms here that apply to us in chemistry. So efficiency is equal to kinetic energy divided by potential energy multiplied by 100, or efficiency is equal to an experimental value divided by the theoretical value multiplied by 100. So with the experimental value, how you would calculate that is from your calorimetry data. Because in order to get that data of like how much water you have, the mass of the calorimeter, the change in temperature, you need to do an experiment. Okay. So this is going to be coming from your EP is equal to EK equations here. Now the theoretical value you're going to get from doing a Hess's law calculation. So that could be the additive principle of Hess's law, where you're adding up some stepwise reactions to get the change in enthalpy, or that could be the formula version of Hess's law, which is change in enthalpy is equal to the sum of the moles of the products times by the molar enthalpy of formation of the products, subtracted with the sum of the moles of the reactants times the molar enthalpy of formation of the reactants. So with calorimetry, it assumes 100% efficiency. Okay, so what that means is all of the energy available in a substance gets converted into useful energy in a calorimetry experiment. However, that's not what happens in reality. Energy is going to get lost. Okay, so it gets lost as heat to surroundings, or it could get lost as light, sound, so on and so forth. Okay, so remember that energy is never actually lost in chemistry. According to the laws of thermodynamics, it just gets transformed from one form into a different form. Okay, so for chemistry, efficiency, it's just how much heat from the reaction heats up the water in a calorimeter. That's a more specific example of what we care about in terms of efficiency when doing calorimetry experiments. Okay, so how much heat from the reaction heats up the water in a calorimeter? And then reminder here, efficiency is never 100% because we have waste energy, which we're qualifying waste energy as the energy in the substance being converted to sound or light instead of a more useful form like heat. Okay. And since efficiency in the real world is never 100%. It also would make sense that efficiency would never be more than 100%. So if you're calculating efficiency and you get a number higher than 100%, you are doing something wrong. All right, so there's two different concepts that apply to measurement: accuracy and precision. Now, they mean two different things here, and what we can do is we can talk about this diagram for a little bit before we go on into the notes. Okay, so in this first picture here, you can imagine that this is a dartboard, bullseye, and the dots are all darts being thrown at the dartboard. Okay, so in this diagram, when your darts kind of land all over the dartboard, okay, that's going to be representing low accuracy and low precision. Okay, now accuracy means like how close did you get to the predicted value or the value that you want. So in darts, you're aiming for the bullseye here. Okay, so if you don't get the bullseye consistently, then you've got low accuracy. Okay, now precision is you're not necessarily aiming for a particular value, but if your measurements all get to, like, maybe not the quote-unquote correct value, but they're all around the same number, then that would be high precision. Okay, so for example here, again, accuracy would be you're hitting the bullseye 100% of the time. That would be high accuracy with this. But with this, since all of these darts, they didn't hit the bullseye, so what we're aiming towards, okay, but they all kind of clustered around the same area. Okay, so we didn't hit the value or the area that we were aiming for. In this case, it's the bullseye, so that's low accuracy, but all of our darts ended up around the same spot, which is high precision. Okay, so for numbers here, let's say you were measuring out the mass of some substance, okay, and let's say that you were supposed to measure out 5 grams of a substance. You were supposed to measure out 3 samples of a specific substance, and they're all supposed to be around 5 grams because you wanted to do 3 trials of some experiment, let's say. But when measuring out the mass, let's say you got 4.83 grams for one of the amounts of the substance that you weighed out. Then for the next one, you got 4.85 grams, and then the next one you got 4.84 grams. Okay, so all of these measurements of a mass of a substance, they weren't the value that you were aiming for, they were way off, okay, but all of these values are kind of around the same number. So this would be an example more particular to chemistry where this would be low accuracy because you didn't get the actual amount of mass of a substance that you were aiming for, which in this example was 5 grams, but all of the masses that you did weigh out of one particular substance, they're all around the same number there. Okay. So for our example of high accuracy but low precision, so again, we're aiming for the bullseye here, and most of our darts are pretty close to the bullseye. So That's the area of the dartboard that we're aiming for. Most of them hit close to or on the bullseye, so that means high accuracy, but we don't get the darts in a specific area, right? They're all kind of scattered around this sort of area, so then that's low precision. Okay, now what high accuracy and high precision would look like is all of our darts hit the area we're aiming for, so the bullseye, and they're all right close in the same spot, so that would be high precision. Okay, so going to our notes here, okay, with accuracy, how that applies to chemistry is we measure accuracy with percent error. Okay, so how far off from the value we were aiming for did we get? Actually, I'm going to say measured with. Percent error. Okay, so like I said, accuracy is how close did you get to the predicted value. Okay, so in chemistry, we would call this the theoretical value. Okay, so another example would be in Chem 20 with stoichiometry calculations. Let's say you predicted the amount of product that you should have gotten out of a reaction. Okay, but when you actually do the reaction in a lab, you should get a little bit less than your predicted value, right? But how close you get to that predicted value that you got from your stoichiometry calculation, right? How close you get to that value is going to change what your percent error is. So if you got a little bit less than the predicted or the theoretical value of product that you should have gotten out of a reaction, right? You got a little bit less, but it's still pretty close to the predicted value. Your percent error is not all that big, okay? However, if you do your experiment and the amount of product that you got was way off from your predicted value of how much product you're supposed to get out of that experiment, then you're going to have a larger percent error because you didn't get very close to the theoretical value that you should have gotten. So that means maybe when you're doing your experiment, some human error came into play. So maybe your reaction, when it was going, you didn't stir it enough to encourage reactions to happen. Or maybe when you were transferring a substance from one beaker or one piece of glassware to another, right, you lost some product in that transfer. Okay. Now, with precision, for chemistry, that has to do with significant digits. Okay, so for example, if we have a value such as 10.21 grams versus 10.211 grams, this number is more precise because it has more significant digits. Okay, so the more significant digits you have, the more precise your answer can be when doing calculations. Okay, so what that means in the context of chemistry is when you're measuring out your reactants, the more digits you're able to get from your instruments. So the more precise your instruments are, okay, the more digits you can get for a value of what substance you're measuring, right? The more digits you have when you're measuring out your reactants, the more digits you can have in your final answer when you calculate how much product you should be getting from a certain amount of reactants, right? So SIGDIGs, when you're in the lab, they come from the precision of your instruments that you're using to measure your reactants or your substances in general. Okay, so example 1 here. We have an acetylene torch is used to heat 1.4 kilogram iron rod if 650 kilojoules of energy is available in the acetylene, and it raises the temperature of the iron rod, which has a specific heat capacity of 0.45 joules per gram degree Celsius, by 300 degrees. What is the efficiency of the torch? Okay, so let's break this down. So our iron rod here, so that is the substance that's undergoing a change in temperature, but it's not undergoing a reaction. So that means that the information related to the iron rod is going to be related to kinetic energy. Okay. Now, with this 650 kilojoules of energy being available in the acetylene, well, when you're running an acetylene torch, you're burning acetylene. So that's undergoing a chemical reaction. So it's potential energy because acetylene is undergoing a chemical reaction. Okay, and then other values we were given was specific heat capacity of the iron rod and the final temperature of the iron rod. We're asked for efficiency. Okay, so let's start off with the iron rod there. So we said because it undergoes a temperature change and not a chemical reaction, this is going to be dealing with kinetic energy. So remember, that's mass times specific heat times the change in temperature. So the mass of the iron rod was 1.4 kilograms. Okay, so for mass, you can either convert kilograms into grams, or you can change the units of your specific heat capacity from joules per gram degree Celsius to kilojoules per kilogram degree Celsius. You could go either way. Okay, so I'm just going to choose to keep it in kilograms. So remember, since we have the prefix kilo in the top and the bottom, that doesn't change the value of this, because kilo, they can cancel out and you'll still have the same value. Okay, so the change of temperature, it says it raised the temperature by 300 degrees. Okay, so my bad, I read it wrong just a little bit before here. So this isn't the final temperature. It tells us that the temperature changed or was raised by 300 degrees. Okay, so raised means that it's a positive 300 degrees Celsius. Alright, so let's calculate this. 1.4 times by 0.45 times by 300, so we get 189 kilojoules. How I know I have kilojoules is because kilograms cancels out, degrees Celsius cancels out, so we're left with kilojoules. Alright, so going back to our efficiency formula here, we already figured out kinetic energy. Okay, we have been given potential energy, so all we need to do is write out our formula and then calculate this. So percent efficiency is equal to kinetic energy divided by potential energy times by 100%. So our kinetic energy was 189 kilojoules, and then our potential energy so that would be that 650 kilojoules. So 189 divided by 650 times by 100 is going to give us 29.0769. And that's percent because the kilojoules cancels out and we're left with percent here. Okay, so looking at our sigdigs, it looks like the number with the least amount of sigdigs is this 1.4. So that has 2 sigdigs, so my final answer needs to be in 2 sigdigs. Okay, so that means my cutoff line is right here. So my final answer is going to be 29% efficiency. Alright, for this next example, we once again have another acetylene torch is used to raise the temperature of a 250 gram iron pipe by 45 degrees Celsius. For this process, 70 or 0.70 grams of acetylene is burned, and the molar enthalpy of combustion for acetylene in an open air environment is negative 1256.2 kilojoules per mole. Determine the efficiency of the lighter as a heating device. Okay, so we're first talking about this iron pipe, and its temperature is raised by 45 degrees Celsius. So the iron pipe isn't undergoing a chemical reaction, but it is undergoing a temperature change. So that's going to be our EK.
You already know anything with math.
Yes. Well, everybody was going to work today.
So EK is equal to mass times specific heat times the change in temperature. So the mass of the iron pipe was 250 grams. Okay. And since it's an iron pipe here, we can just use the specific heat capacity from the previous question because it's made out of the same metal. And since I kept my mass in grams, I'm going to keep this as joules per gram degrees Celsius. And then change in temperature. The question said that the temperature was raised by 45 degrees Celsius, so that's giving us the change in temperature. So 250 times 0.45 times 45. That's going to give us 5,062.5. Okay, so for our units, grams cancels out, so does your degrees Celsius, so we're left with joules here. Oh. Alrighty, so we have kinetic energy, now we need to figure out potential energy. Now for potential energy, remember that potential energy is equal to the change in enthalpy, which is equal to moles times the molar enthalpy of, and since our reaction here is combustion, I'm going to go molar enthalpy of combustion for acetylene. All right, so we were given the molar enthalpy of combustion for acetylene in the question. So we already have this, and we were given a mass for acetylene, but not the moles. So we need to spend some time on figuring out how many moles of acetylene that we have before we're able to figure out the potential energy of this reaction. Okay. So I'm gonna have to put that over here just so I have enough space for everything. So moles is equal to mass divided by molar mass. So our mass was 0.70 grams. All right, so to figure out the molar mass of acetylene, you can look at your periodic table to figure out what the molar mass is. If you're thinking to yourself that you don't know what the chemical formula of acetylene is, what you can do is you can go to your data booklet on page 4. Another word for, or another name for acetylene is ethine. Okay, so the chemical formula for acetylene is just C2H2. So then the molar mass of that is going to be 26.04 grams per mole. So that's going to give us 0.02688, goes on forever. Okay, so there's our moles of acetylene. Okay, so now that we've figured out that, we can keep on keeping on with this. So our moles here, that's going to be what we just calculated out. But another thing that we're going to want to consider with this calculation here is the fact that this is going to be an exothermic reaction because acetylene is being burned. Okay, so remember when we did that heat lost is equal to heat gained. Now the left side of this equation here is the potential energy side. Okay, now when we had an exothermic reaction, we put the negative on the potential energy side. Okay, and we're going to have to do the same thing here. So we're just going to have to put a negative here. Okay, because otherwise, if we don't, we're going to get a negative potential energy. And once we put this into our percent efficiency calculation, so EK divided by EP times 100%. So if we don't put in this negative here, then that's going to cause our potential energy to be negative, which will mean our percent efficiency will come out negative. Now, it doesn't make sense for percent efficiency or the efficiency of a process to be a negative percentage, okay? So that's another reason why we need to have this negative here. So our moles, 26.02688, goes on forever. Molar enthalpy of combustion, that's at negative 1256.2. And the units are kilojoules per mole. Okay, now I gotta get rid of this so that I have enough space. Okay, so we're taking this entire raw number, multiplying it by that negative 1256.2. Oh, and then I didn't write the negative here in my calculation, so all I'd have to do to fix that is just go times by a -1 to fix it. Okay, so we got 33.7688, goes on forever. Moles cancels out, so we have kilojoules. Okay, so that is our potential energy. So we have our potential energy, we have our kinetic energy, so we've got everything to figure out percent efficiency. All right, so our kinetic energy, that was that 5,062.5. And what was that in? Was that, okay, so that was in joules, okay? Now, I'll finish writing this and then I'll point out the issue that we're going to be having here. So our potential energy was at 33.7688, goes on forever, kilojoules. Okay, so notice that our units don't match up here. Okay, so I'm thinking to myself, we could convert either our kinetic energy from joules into kilojoules, or we could convert our potential energy from kilojoules to joules. Either way, it's gonna give you the same answer. Okay, so pick one way, stick with it. Okay, I'm gonna choose to convert kinetic energy from joules to kilojoules. So what that means is we just divide by 1,000, and that's gonna move our decimal point over 1, 2, 3 spots to the left. Okay, so that's going to turn this into 5.0625 kilojoules. Okay, and then times by 100%. So we're going 5.0625 divided by answer times by 100. And we get 14.9916%. All right, now looking at our given numbers here, it looks like the number with the least amount of sig digs is a 0.70, so that has 2 sig digs in it. So my final answer needs to have 2 sig digs in it. Okay, so the cutoff line is right here, so that's going to be 15%. All right, now let's move on to thermal stability here. All right, so thermal stability, what is it? It's the ability of a compound to resist decomposition when heated. So what that means is when a compound is able to resist decomposition, that means that you're going to have to add a lot of energy in order to cause it to break down or to decompose. Okay, you have to add energy to something in order to break those bonds, and the more energy you have to add in order to break the bonds, the more stable it is. Okay, so what this means is the more positive the molar enthalpy of decomposition is, the more thermally stable the compound is going to be. Okay, so the key here is that we're using molar enthalpy of decomposition. So you're going to find that on page 4 and 5 of your data booklet, but there's some work to be done. Okay, so remember that page 4 and 5 of your data booklet, they give you the molar enthalpies of formation. Now to go from formation to decomposition, like they're just opposite processes. So what you need to do to these numbers is, if you have a negative value for molar enthalpy of formation, you just take that negative and then flip it into a positive. So for this first compound here, so aluminum oxide, the molar enthalpy of formation is negative 1675.7. Now the molar enthalpy of decomposition would be positive 1675.7, and that's in kilojoules per mole. Okay, so key thing to remember, you can find them on page 4 and 5 of your data booklet. And maybe I'll just adjust this a little bit. Oop, that didn't do what I wanted it to do. Let's move this over a little bit. So you can find the molar enthalpy of formation on page 4 and 5 of the data booklet. You need to flip the sign to get molar enthalpy of decomposition. Okay, so if molar enthalpy of formation is negative, flip it into a positive to get molar enthalpy of decomposition. If molar enthalpy of formation is a positive value, flip it from positive to negative to get your molar enthalpy of decomposition. Okay, so again, remember, the more positive your molar enthalpy of decomposition is, that means the more energy that it's going to take in order to decompose that compound. Okay, so the least thermally stable value here would be this negative 1000. The most thermally stable value here, or compound here, would be this positive 1000. Okay, so what this is saying is it would take 1000, assuming the units are kilojoules per mole here, it would take 1000 kilojoules per mole of a certain substance, okay, in order to cause it to decompose. Okay, so again, the more energy you have to put into something to get it to decompose, the more stable or thermally stable it is. Okay, so example 1, which compound is more thermally stable? Okay, iron 2 oxide or iron 3 oxide? So if the molar enthalpy of formation of iron 2 oxide is negative 272 kilojoules per mole, then the molar enthalpy of decomposition is positive 272. Now, if the molar enthalpy of formation for iron 3 oxide is negative 824.2 kilojoules per mole, then the molar enthalpy of decomposition of that same substance is positive 824.2 kilojoules per mole. Okay, so again, we're looking at which value is more positive. that will tell you which compound is more thermally stable. Okay, so here we know, obviously, iron 3 oxide is more stable because its molar enthalpy of decomposition is 824.2 kilojoules per mole. So that means it takes this much energy per mole of iron 3 oxide in order to break it down, which is more than what's needed for iron 2 oxide. So I'm going to say iron 3 oxide is more thermally stable. Okay, so I'm going to be writing down some stuff that I've been saying, just haven't written it down here. So again, whichever value for molar enthalpy of decomposition, so it's very important that you're using molar enthalpy of decomposition and not formation, is biggest or more positive is the most thermally stable. The more positive the number, what that means is that the more positive the number is, the more energy you need in order to break the compound down. So the more positive the number of molar enthalpy of decomposition, the more energy is required to break that substance down or to decompose it. Okay. Therefore, it's going to be more thermally stable. So, I'm repeating this quite a bit because it's important. Can I fit in stable? No. Okay. All right, example 2. Which compound is more thermally stable? Nitrogen dioxide or nitrogen monoxide? Okay, so first things first, let's write out our substances and figure out what the molar enthalpy of decomposition is for both of them. So let's go to our data booklet. So remember, these are organized alphabetically. So nitrogen dioxide is right here. So the molar enthalpy of formation is positive 33.2 kilojoules per mole. So that means decomposition, we just need to flip the sign. So negative 33.2 kilojoules per mole. Okay, now for nitrogen monoxide, so that's just right underneath nitrogen dioxide. That was positive 91.3 for molar enthalpy of formation, so we just flip the sign. That's going to be negative 91.3 kilojoules per mole. Okay, so we got to ask ourselves, which one is the bigger number? Now, since both of these are negative numbers, right, you could also ask yourself, okay, which one of these numbers is closest to 0 to help yourself out. Okay, so ultimately, nitrogen dioxide has the higher molar enthalpy of decomposition. So out of these two, nitrogen dioxide is more thermally stable. All right, example number 3. Place the following compounds in order from most stable to least stable. Okay, so same process. Let's figure out our molar enthalpies of decomposition. And the units will be kilojoules per mole. Okay, so dinitrogen tetroxide, let's find that. So I'm finding it right here. So the molar enthalpy of formation is positive 11.1. So then we got to flip the sign. So that's negative 11.1. All right, barium carbonate. So that is right here. So we got to flip the sign. So that's going to be positive 1213. All right, hydrogen sulfide gas. Right there, so it's negative 20.6 for molar enthalpy of formation, so let's flip the sign. Positive 20.6. And then ethyne. So let's look that up. So that's going to be positive 227.4. So we've got to flip the sign. Okay, so if you're wondering why this number is different from the molar enthalpy of combustion from our previous question back when we were talking about efficiency, the example 2, it said that the molar enthalpy of ethyne, which is the same thing as acetylene, was negative 1,256.2 kilojoules per mole. Keep in mind that that negative 1,256.2 is for combustion of ethyne or acetylene. This is just for decomposition of ethyne. So there's two different reactions going on. That's why there's two different molar enthalpies, is because they talk about two different reactions. Okay. So we're asked to go from most to least stable. So I'm going to write most stable and then least stable we'll say somewhere over here. Okay, so basically we're going from the most positive number to the least positive number. Okay, so that looks like barium carbonate is going to be the first one. I'm going to put boxes around these just to make it a little bit easier. Okay, so barium, actually, you know what, I'm not going to write it out. I'm just going to do the formula. Carbonate, so carbonate likes to have a -2 charge. Barium's 2+, so that's already balanced. Okay, what's our next one here? Looks like hydrogen sulfide gas. So next, so H2S, we'll put it as a gas. Okay, and then our next one is going to be dinitrogen tetroxide. And then we have ethyne, which is the same as acetylene, which is C2H2. So again, if I looked that up, there's where the formula is for acetylene or ethyne. Okay. So I was going to move over that least just to cozy it up to ethyne, but this will be fine.